we start. We still have only 3 students, so I don't know. So how to proceed. So today I continue the exercise for the last time. That is the support vector machine. And I think all of you were here, so that's fine. And also I would like to cover the support vector regression for regression analysis and also the R examples. So those are the 2 things to do. And starting next week, we do a neural network. I think we don't have much time, so probably 1.5 days, or maybe 1 to 1.5 days for the ideas theory, and then the other 1.5 days for practice and the lab session. Yeah, I don't know what. Yeah, maybe I explain the support vector regression first. Then possibly, hopefully, that we would have we will have one or two more people to discuss the exercise. Okay. Yeah. Oh, there, Hunter, did you submit your final project plan or not yet?
No, not yet.
Not yet. Okay. Just do it when you're ready.
Yep.
And yeah, I think your presentation is still in May, so I think it's still fine. Okay, so I will share the screen to discuss the support vector regression. That is the regression version of support vector machine. So often the same method is available for classification and regression. For example, the neural network is one case and tree-based method is another case. But the support vector regression is a little bit interesting because the algorithm is similar to support vector machine, but slightly different. At least in terms of modeling idea, slightly different. So support vector machine is a large margin classifier. So the idea is we map the original predictors into higher dimensional space. Then in higher dimensional space, it's easier to separate the cases. So ideally, that we can perfectly separate the 2 groups, the label with 1 and label with -1. And not only just dividing it perfectly, we make the margin largest so that the test error gets smaller. So that was the idea of support vector machines. And actually, yeah, we have slightly more complicated rule if we allow some errors, but basically that's the idea. So next we consider the support vector regression. So support vector regression, in support vector regression, the setting is this. So originally we have the predictor X and response Y. So Y is a real number. And suppose there are n observations. Then that we consider to map this predictor to a higher dimensional space. So, sorry. Capital M is larger than P. Usually much larger. And we consider the model here. So, of course, if X becomes phi of X, then we have more possibilities. For example, if X was X1, X2, and maybe this map phi is X1, X2 to for example, x1 square, x1, x2, x square, then at least this can represent more complicated pattern than usual linear model. Then, but this is just, the same as the radial basis functions, right? So in polynomial regression or radial basis function, we did the same thing. And support vector machine has additional the modeling idea. So that is kind of similar to the rich regression. So we minimize the error size. That is the first term of this objective function, and also the lambda constant times the length of beta square. So that is basically the beta 1 square, beta 2 square, up to beta m square. Usually the constant term is excluded. So basically we want to minimize the error size. The v is typically in linear regression, that is just the v of x is x square. So we minimize the error size, but also we want to have a simple model. So we penalize the size of the coefficients. So similar to rich regression. And the difference between rich regression and the support vector machine is here. So v of z is a special function, which is equal to 0 if the z is within negative epsilon to epsilon, and the absolute value of z minus epsilon otherwise. So it's easy to see this, and this function is the v of z. So y is equal to v of z. Maybe y may not be good. So maybe w is equal to, maybe u is equal to. So basically, we don't penalize error if error is within negative epsilon to epsilon. But it will penalize if it's larger than this. But only linear penalty. So in usual least square is this case, least square penalty, if epsilon is if epsilon is larger, the penalty is much larger, so epsilon square. But in this, the lasso regression, the support vector regression, the penalty is smaller. So it's similar to so-called quantile regression. So only the penalty is linear, and also it's so-called epsilon sensitive penalty. So if it's less than epsilon, the penalty size is 0. Yeah, and here this epsilon, I mean this size epsilon, and also the lambda in the coefficient of beta. So these two are hyperparameters. So we have to decide, maybe based on the cross-validated error within the training set. So that is the support vector regression. So we have the hyperparameters, and the basically it automatically looks for the best complicated model. And here is the idea of the support vector regression. So, okay, at first we map X to the higher dimensional space, so we can identify the complicated relationship between X and Y. And this red line is a kind of fitted value. So this represents the basically beta times the phi of X. Then this is this tube. So this is this pink area is the so-called epsilon tube. So if the observations are within this epsilon tube, basically we don't have any penalty on these observations. So small fluctuation of the data does not really matter for this rule. But once excuse me. observations are above this tube, then so these affects the error size. So basically that we consider the distance between these to this tube, and actually this does not really matter, but this distance. So these distances matter for the the objective function. So basically these dots are the optimal function, optimal parameter is not affected by the points within the tube, but it's affected by the points outside of the tube. So that is the idea. So, okay, so only a few observations are out of this tube. So we expect that if the fit is good, then most observations are within this tube. So only few X values affects the estimation results. So that means we can believe that this rule is not super complicated, because a few observations almost determine the entire rule. Right? So it's a little bit strange that only a kind of outliers determines the regression curve, but this is the idea of support vector regression. Okay. Do you have any questions on support vector regression? So in support vector regression, so it does not require you to specify what function of X is useful. So just you specify the kernel, then support vector regression automatically the search for this complicated relationship between X and Y. Yeah, if you don't have any questions, then we go on to the lab session for support vector regression. Yeah. So in this example, in this section, we use the Boston dataset. That is one of my favorite dataset, and which has 506 observations and 14 variables for the house price in Boston suburb. Each observation represents a town in Boston, and the variables, predictors, are some economic variables, demographic variables, and environmental variables, such as the NOx level. And our objective is to predict the median house value by other predictors. And we set the training set and the test set. I just use 50% of observations as training set at random, and the others as the test set. So 253 observations each. So I just set seed for reproducibility. And at first we try this prediction job by the baseline model. So I use the linear model, and we use the stepwise selection. So basically this is the backward selection. We start with the full model. Possibly we add some variables again, so it goes both ways. But basically, starting with the full model, that we reduce the size of the model to get the best model. And this is the final model. Final model have in total 12 predictors. So actually, the most of the predictors, as originally we have yeah, I don't know, 1, 2, 3, yeah, 14 variables included. So we have 13 predictors. So it chooses most predictors. And training error size in terms of RMSE by this model is 4.65. And the test error is 9.38. And now we try the support vector regression. So support vector regression can be done just by SVM function again. So basically the algorithm automatically adjusts if the response variable is continuous scale, I mean numeric scale variable. So we use training set. And the default for support vector machine function is radial kernel. And with some default value of cost and this function epsilon. Gamma is, I think, the parameter in the radial basis function, the coefficient of the radial basis function on exponential part. You can check the help of SVM function in R. Then we can get the training error of 3.35 and the test error of 8.93. So support vector machine is more complicated model, so it can deal with more complicated patterns. So we have overfitting. So training error is very small. Originally that was 4.65. It is reduced to 3.35, but the test error that doesn't get much smaller. So 9.38 to 8.93, still 5% reduction. So it makes sense, but not much better. So by this automatic procedure, the training error, the test error has been improved by about 5%. So now that we optimize some hyperparameters, so I didn't show all the details, but I found that cost of 0.1 and the epsilon of 0.5 looks good. Possibly you can also change gamma to make it better. And now that we got the training error of 6.67. Okay, this is actually larger than the previous one, but the test error is 7.68. So it improved a pretty large amount. Or 8.9 was original one. 8.94 is the previous result, but that becomes 7.69. So that is, I think, more than 10%, maybe 15% smaller. So that is a good achievement. So basically, the optimizing these parameters to avoid overfitting. So the training error is more realistic number. So it's larger, but that doesn't matter. Anyway, we know the training response values. So important thing is test performance, and the test performance improved a lot. Yeah, this is just some descriptive statistic of actual Y and the predicted Y for training set. So you can see the positive relationship. We have some problem here. I think that these values are censored. I mean, these are truncated at 50. So some median house value exceeds the $50,000. So this data set, the truncate at 50. And I don't know. So this, yeah, it's a kind of outliers, but yeah. And for test error, we have the same thing. The Y is here, Y hat is here, and the correlation is slightly lower. I think the it looks relationship is vaguer than the previous one, but still it has some meaningful positive correlation. Yeah. So that is the support vector machine for support vector regression for the continuous response variable. And I also tried the kernel, linear kernel, to predict this. So this is similar to so usual the regression model, so linear kernel. But still the model is different because this is epsilon sensitive and some cost. And here the cost is small, that is C is large. So and epsilon is small. That is the almost similar to this error function. So this should be somewhat similar to linear regression. So we can try this. And actually, the training error is this, and the test error is this. So actually, this is still the better than yeah. So it's still the better than the linear regression. So with automatic procedure, without any variable selection, it performs slightly better than linear regression. Yeah, so this is the support vector regression. Do you have any questions?
I was a little bit late.
Yep.
What triggers in this? What you're doing right here? You got SVM. You have the formula, the data, the linear, the cost. So to make it a SVR, it's the epsilon is the trigger.
Epsilon is the trigger. I mean the hyperparameter in the error function. So
no, okay. I guess the main question is I was watching what you were doing there, and I was going, how the first SCM linear we do gives us a line. Now this is going to give us a path. It's got to be because of the epsilon. And so, I want to make sure I understand what I'm looking, where it's coming from. Okay.
So maybe you want to know what is epsilon, and also what triggers the R language to distinguish classification problem and regression problem.
I'll go back to it.
Yeah, so epsilon is a hyperparameter which appears in the function to evaluate error. So basically, the error size less than epsilon is ignored in support vector regression. And the what makes the R language to distinguish classification and regression? That is simply the response variable. If response variable is binary, then it runs the support vector machine, and if continuous, the support vector regression. Yep. And yeah, so and epsilon does not trigger anything, I think. So we have some default value of epsilon, and we can just change it. So that is similar to like cost parameter or some other coef zero parameter. So maybe I stop sharing the screen. Yeah, so yeah, for epsilon, the default value is 0.1. So if you don't specify epsilon, still the SVM function runs support vector regression with epsilon equal to 0.1. Yeah. Okay. Okay, so then we continue the previous exercise on support vector machine. Okay, so we have still about 50 minutes, so I think we have enough time. And next, how to group it. So last time, the Nathan, Victoria, and William was the one group. So Nathan, Victoria here, and William all of you are here. And another group is Erica, Thomas, and James. But today Thomas is not here. Maybe I put the Hunter in that group. Okay, so then you can discuss the exercise. And I think there's some of you the saved code, so I think that you can just continue. Just a moment. I think it's a little bit complicated to set up the group. Nathan and Victoria and William. Okay, so then Erica, Hunter, and James. Okay, we start. So you can discuss until like maybe 7:30. at least. Okay. So exercise 9, yes. Exercise for April 3rd.
Professor, you might be muted. I'm not sure if you're talking right now.
Thank you. Thank you. Yes, so first we import the library for data and the import E1071 for support vector machine. So this is the data. So you can see these variables, and the purchase is the response variable. I think that here, yes, the purchase. So we have the two stores to purchase some product, two brands for orange juice, and which brand that they purchased, that is the response variable. And actually this question, the how to set the training and the test set affects the result of this model. So just I use the set seed 412 to make the training set and the test set. So training set oj.r, test set oj.s. And first, the support vector machine with radial linear kernel with the cost parameter equal to 0.01. And this gives the this table. This means the 135 observations are classified incorrectly out of 800, and the training error of 0.168. Probably this number ranges from maybe 0.15 to 0.21 or 222, depending on how to set the training set and the test set. It's just random. And the test error is here. You can see this is 44 over remaining number of observations. Actually, the test set has 270 observations. So this is 44 over 270. And actually, just by chance, this is smaller than the training set. So probably the test data set has a better property than training set, just by chance. And then we tune the parameter. We can use the range is equal to list of cost is equal to the range of the numbers. So I tried these 1, 2, 3, 4, 5, 6 numbers. And it sounds that the 10 is the best parameter. So this 10 is the best parameter. And the best performance is 0.175. This sounds a little strange because the previously already the training error is the 0.168, but this is actually the cross-validated error. So cross-validated error in training set. So this is almost similar to test error, but we are using only training set, and we choose the best parameter in the training set. So this is, slightly better than test error on average, but it's basically similar to test error. And these are the summary. And you can see that this one is the best parameter. And we can calculate the training error and test error again. So training error is 0.16 and the test error is 0.159. So this is just slightly better than the previous result, maybe 0.1593, and previously 0.1629. So it's pretty similar, but slightly better. Yeah, so we are using the same test set. So we don't have any, unlucky things. So when you compare test performance, they're using the same test set or using the same cross-validated set, improves the situation a little bit. For example, if you do cross-validation for support vector machine and also tree-based methods, you use different package. If you use the same validation set, the same randomization, then your evaluation is more accurate. Okay, so next, the radial kernel and the kernel radial, and I optimize this cost and also the gamma value. So radial basis kernel is the exponential of negative gamma times the u minus v, where u and v are the two predictor vectors, and square. So this gamma is a hyperparameter. So exponential. And if we optimize two parameters, basically they do the grid search. So they look for the smallest error size that is probably here, maybe not, yeah. So cost value of 1 and the gamma value of 0.01 is the best one. So based on this, training error is 0.168, test error is 0.1444. So this is actually the best so far. And the polynomial kernel, the coef 0 and the cost, these are parameters to optimize. And also you can optimize D. I tried 2 and 3, and 3 isn't better than 2. So I didn't try 4 and larger, but you can certainly optimize it. And it sounds the coefficient 0 is, if coefficient 0 value is too large, it sounds to cause some trouble. So the the inner product for polynomial kernel is this. So it sounds that coef 0 is large, that these values are very similar regardless of u and v. So probably the observations are very singular, almost singular, and it causes some problem. So sometimes the larger coef 0 value is better, but we have some convergence problem when we optimize. So that is, the common problem in optimizing hyperparameters. So I don't know what is the best answer to solve this, and we are not sure what's happening in the feature space. But okay, but in this trial, actually it converges successfully, and the best performance is 0.17 with cost of 0.1 and coefficient 0 of 1000. 1.717, 0.17. I think that value is found here. Actually, this coef 0 value is largest value we tried. So if we try 5,000 or 10,000, possibly it's better. But I stop here. Maybe you can try it. Maybe it converges or not. And the training error, the training error. Training error is 1.6125 for this case. It's smaller because it's not cross-validated. And the test error is 1.5159, 0.1593. So this is actually exactly the same as the linear kernel with best parameter, just by chance. And the sigmoid kernel, it sounds sigmoid kernel does not work well. The sigmoid kernel, you can see the formula is the inner product is the hypertangent of the gamma times the u transposed v plus coef 0. So either gamma or coef 0 is a parameter. And I set just gamma is equal to 1. That is, I think, default value. So I change coef 0 value. So yeah, we tried this, but it sounds it does not work well. And the best performance for cross-validated error is 19375 with parameter coef cost is equal to 0.1, coef 0 is equal to 0. And the training performance is 0.206 and the test performance is 0.211. So in my experiment, the radial kernel has the smallest test error. We have to decide based on test error. But it's similar to the performance of linear kernel and also polynomial kernel. So depending on your randomization of the training and the test sets, maybe you choose the linear kernel or polynomial kernel. And I think the sigmoid kernel that performs consistently worse than the other three for this example. Okay, so that's it for today. Do you have any questions?
No, I think you answered them. Thank you.
Yeah. So just the important thing is for machine learning models, the more tasks are automatic. We don't have to choose variables. And yeah, but still we have to tune hyperparameters. So if you put the data in some package, but if the hyperparameters are not optimized, then you didn't get the best result of the model. So you have to explore how to optimize parameters. Sometimes we have convergence problem and some other problems. Yeah, so just I would like to tell you that. Next time we study neural network. Okay, so see you next Monday.